This summer, I didn't shower for 2 months. Now, you're probably wondering how I'm going to turn my lack of personal hygiene into a talk about climate change. Over the past 3 years, I've worked with the MIT Glaciers group studying how ice moves and breaks. But there's only so much you can get out of staring at a computer screen. So I decided to get up close and personal with glaciers this summer. Very personal. That's me, 7 weeks into not showering, underneath the Llewellyn Glacier in Canada. This summer, I had the privilege of joining the Juneau Icefield Research Program as a student and spent 8 weeks on the showerless Juneau Icefield learning how to become a field glaciologist. Other than someone who doesn't shower for extended periods of time, which, for the record, is not a job requirement, a glaciologist is someone who studies glaciers. There are a whole bunch of different flavors of glaciologist, from field scientists to theorists to computer modelers. I normally fall into the try software that doesn't work the first time around and bang my head against the computer repeatedly until it somehow works category. Glaciologists also weigh in on policy, including the Intergovernmental Panel on Climate Change, also known as the IPCC, to inform reports about the contributions of ice to sea level rise. According to the IPCC special report from 2019, ice is the dominant source of global mean sea level rise and contributes significantly to uncertainty in projections past the year 2100. The chart above shows sea level rise projections for 2 emission scenarios, with the shaded area representing the uncertainty. Under a high emissions scenario, sea level could rise anywhere from 2 to 5 meters by 2300. Why is the uncertainty so great? Because we lack key information regarding the processes through which ice flows and breaks. Before we dive into climate change, what exactly is a glacier? A glacier is a large body of ice that persists year-round and moves downslope under the influence of its own weight and gravity. Snow falls high up on the mountain, and once it builds up enough, the weight causes the ice underneath it to flow downhill. Glaciers grow when they receive more water via snowfall than they lose via melt or icebergs breaking away, and shrink when the reverse is true. An ice sheet is a body of ice larger than 50,000 kilometers squared. There are only 2 ice sheets on Earth, the Antarctic and Greenland ice sheets. Ice moves. It doesn't just slide along on the rocks underneath it, it deforms under its own weight, splooging out from its thickest point like honey piling up on a cracker. The Taku Glacier in Juneau was moving a little over 2 feet per day in the center when this picture was taken. This movement isn't visible to the human eye, but when sped up over weeks or months, ice moves surprisingly fluid-like compared to our standard reference point, which is normally floating in our drinks. Glaciers and ice sheets move like honey, a viscous fluid flowing outwards from the point of thickest ice. What was surprising to me when I first started in the field is that not only does ice flow, it flows like rivers, with fast-flowing ice streams draining the slower-moving interior ice. Ice even has drainage basins and tributaries feeding the ice streams. The fastest ice we see is present on ice shelves, the floating extensions of glaciers and ice sheets. When I first became a glaciologist, my only exposure to glaciers was articles in the news. Like this article about an iceberg the size of San Francisco, or this one about an iceberg the size of Luxembourg, or this one, or yeah, there are a lot of these. 2 takeaways from all these news stories. Icebergs calve or break off from Antarctica frequently, and scientists like to state iceberg sizes in anything other than standard units. The Delaware-sized iceberg is my personal favorite. Before I became a glaciologist, every time I saw an article like these, I thought it had something to do with climate change, and this made me really sad. So let's take a look at what iceberg calving events mean for future sea level rise. Before we begin, let's take a step back and get an idea of scale. To be fair to scientists, it is hard to get an idea of scale with just numbers. When looking at this picture, an iceberg the size of Delaware doesn't seem all that big after all. Where are these Delaware-sized icebergs coming from? Ice is breaking off of ice shelves, the floating extensions of the Antarctic ice sheet. At some point, the ice transitions from being on land or grounded to floating as it flows from the thickest point inland out into the ocean. We call this boundary the grounding line. Iceberg calving events don't actually directly cause sea level rise because they are already floating when the iceberg breaks away from the ice shelf. As soon as the ice crosses the grounding line, it begins to float. It is already displacing the water it will contribute to sea level rise. Iceberg calving is a natural way that glaciers and ice sheets lose mass. One thing you'll notice in these maps is that the larger ice shelves tend to be confined on the sides. The friction between the edge of the ice shelf and the floating ice creates a resistive force that slows the flow of ice across the grounding line and into the ocean. Ice shelves provide a necessary speed bump to ice velocity and prevent inland ice from draining the thicker interior ice sheet. If we remove part of the ice shelf through an iceberg calving, part of that resistive force is lost, and the flow of ice across the grounding line will speed up, contributing to sea level rise. We have seen this speed up happen when ice shelves have collapsed. Most notably, the Larsen B ice shelf on the West Antarctic Peninsula disintegrated over the course of weeks in 2002, causing the glaciers that fed it to speed up. While these calving events are natural and not necessarily caused by climate change, we are still unsure of the warming ocean's effect on the frequency of calving events, or how future icebergs could affect the resistive stresses that prevent grounded Antarctic ice from draining. Now, there's another Antarctic subject you may have seen in the news recently, including this article from my parents' local paper just last week. Kind of apocalyptic, right? The so-called Doomsday Glacier is Thwaites Glacier, which is located in what I like to call the armpit of Antarctica. Thwaites is a little smaller than the state of Nebraska, or the size of 3.6 times 10 to the 7th football fields for the Americans in the audience. Thwaites is currently losing more mass via melting and iceberg calving than it is gaining via snowfall every year. This means that it is shrinking. Every year, Thwaites is losing 50 billion tons of ice, which is enough to cover Massachusetts in almost 6 feet of ice, or Delaware in 31 feet of ice. The media has labeled Thwaites as the Doomsday Glacier due to a potential instability that affects ice sheets. This is because the bedrock underneath Thwaites slopes inland, meaning that the glacier gets thicker at the grounding line as it retreats. Remember the honey piling up? The higher you pile up the honey, the faster it flows. If the glacier's grounding line retreats on this type of slope, we've got our inland slope here, grounding line is here, retreats a bit, it's now thicker. That means it speeds up. It retreats a little more, it's thicker, it speeds up, retreats more, thicker, and thus the positive feedback loop is born. This is called marine ice sheet instability. Now, if we look at the bedrock underneath Thwaites, we can see that the majority of it is below sea level and sloping inland, making it vulnerable to a runaway retreat. And Thwaites is already retreating. Thwaites looks pretty small compared to the rest of Antarctica, only the size of 29.7 Delawares. So why is it a doomsday glacier? Going back to the ice streams and drainage basins, Thwaites and its direct neighbors drain 32% of the West Antarctic ice sheet. Its collapse will have ramifications for ice speed across many major ice shelves. If we lose that resistive force that Thwaites provides, the ice upstream of it will quickly drain, increasing sea levels. In addition, there are deep sea channels underneath Thwaites that allow warmer ocean waters to directly undercut it at its grounding line and facilitate melt and thinning. Thinner ice provides less resistive force to upstream flow. These factors have caused scientists to label Thwaites and its neighbors as the weak underbelly of the West Antarctic ice sheet. A total collapse of the West Antarctic ice sheet would raise global sea levels by 3.3 meters or 10.8 feet. This is what that would look like in Boston. MIT, Fenway Park, and a multitude of other historic Boston landmarks would be partially submerged and lost. So, is the Doomsday Glacier really hanging on by its fingernails? Well, we don't entirely know yet, and that's what we're working to find out. The International Thwaites Glacier Collaboration is a coalition of scientists from the US and UK across 8 different projects studying every aspect of Thwaites, from the bed to the ocean to the geologic history of its flow. These scientists are trying to answer two questions about Thwaites. How much ice will be lost, and how fast will it happen? At this point, we know that it is unstable, but we still don't know when a potential collapse might happen. The good news is, a total collapse of the West Antarctic ice sheet would take centuries to millennia, so it likely won't happen in our lifetimes. But Thwaites Glacier might still collapse in our lifetimes, and we will likely see more ice shelves collapse around Antarctica. Well, that's all rather depressing. So what can we do? That's where this comes in. We need to better understand our glaciers to know the impacts their loss will have on society and when that impact will occur. My research focuses on answering fundamental questions about how ice breaks and what effects iceberg calving will have on the upstream velocity of ice. This information can then be used to improve the accuracy of glacier and sea level rise models. A lot of the uncertainty in sea level rise projections comes from a lack of constraints on the underlying physical properties of ice. We are still answering questions such as, how hard do you have to pull ice before it breaks? And what is happening at the glacier bed? It's hard to answer these questions in the lab because glacier ice deforms over timescales we cannot replicate. And it's hard to answer these questions in the field due to glaciers' remote locations, including the lack of access to showers. Satellite data has revolutionized the field of glaciology, allowing scientists to monitor glaciers from the comfort of their own homes. But we always need more data and higher data resolution. The Juneau Icefield Research Program has, with the help of its students, taken a continuous record of snowfall over the Juneau Icefield in the last 70 years by digging these large holes in the snow. We dug these holes until we hit last year's snow line. The entire depth of the pit, which was often 6 meters deep, was snow that fell in 1 year. With long-running field observations such as these, we capture the effects of a warming world on our glaciers and ice sheets. With better data, we can better understand the immediate impacts of climate change and support the communities that will be most affected immediately rather than waiting for disaster to strike. Finally, we desperately need to reduce emissions. In this chart, the red line on the top is sea level rise under a high emission scenario, and the blue line on the bottom represents sea level rise with aggressive emission reduction measures. Even under a best case scenario, we will still see up to ½ a meter of sea level rise by the end of the century. The Mendenhall Glacier, which is the most well-known glacier of the Juneau Icefield, has already retreated over 1.5 miles in the 20th century. At a middle-of-the-road emission scenario, the Juneau Icefield is completely eliminated by 2200. Climate change is happening, and it's affecting us now. We have seen it happen in our lifetimes. But there is a way to reduce future harm due to sea level rise. The faster we can reduce emissions, the better the outcome will be for our glaciers and the communities affected by them.